Okay, I'd like to go over the review for the second midterm. Let's start with the first question. We want to find all values of x where this function, f of x equals x squared minus x over x squared minus 1, is undefined, and classify each as a hole in the curve or a vertical asymptote. So we recall from class that a rational function like this, a polynomial divided by a polynomial, is defined everywhere except where its denominator equals 0. Let's go ahead and take this function and factor both the numerator and the denominator. So the numerator, x squared minus x, we always look for the easiest kind of factoring, first common factor, and we can certainly pull an x out of both those factors. And we're left with an x minus 1. X times x is x squared. X times minus 1 is minus x. And the denominator, that's difference of squares. So x plus 1, x minus 1. We said that this thing is defined everywhere except where the denominator equals 0. And that happens, for just a second here. The denominator equals 0 when either this factor is equal to 0 or that factor is equal to 0. So if x plus 1 equals 0, that means that x is equal to negative 1. And if x minus 1 equals 0, that means that x is equal to 1. Now, I will tell you right away that one of these is a vertical asymptote and one is a hole in the curve. We recall that we have a hole in the curve if we can factor out the factor on the bottom with a factor on the top. So we can cancel the x minus 1 with a factor on the top. And so x equals 1 is just a hole in the curve. And the x plus 1 equals 0, there's nothing in the numerator to factor it with. That is a vertical asymptote. We have a vertical asymptote at x equals negative 1. And that's it for the whole question. Let's move on to question number 2. So for each of these following functions, find the horizontal asymptote if the function has one, or the slant asymptote if the function has one, or if the function has neither a horizontal nor slant asymptote. We'll explain why. So in this first question, we have an x squared minus x over an x squared minus 1. It's basically the same curve we had up here. We can see that the degree of the numerator is a 2, and the degree of the denominator is 2. So degree of the numerator is 2, and the degree of the denominator is 2. The largest power of x on the top is 2. The largest power of x on the bottom is 2. When the largest power of x on the top is the same as the largest power of x on the bottom, it does have a horizontal asymptote. And to get the horizontal asymptote, you just take the coefficient of the largest power of x on the top. So the number in front of the x squared is an invisible 1. And the number in front of the x squared on the bottom is an invisible 1. 1 divided by 1 is 1. Y equals 1 is the horizontal asymptote. Let's take a look at part B. This time the degree of the top is 2. You can see 8x squared there. And the degree of the bottom is 3. When the top has smaller degree than the bottom, or equivalently the bottom has larger degree than the top, then we again do have a horizontal asymptote, and that horizontal asymptote will always be y equals 0. So when the degree of the denominator is bigger than the degree of the numerator, it will have a horizontal asymptote at y equals 0. Let's take a look at this third one. You can see that the degree of the top is 2, and the degree of the bottom is 1. When the degree of the top is exactly 1 bigger than the degree of the bottom, so 2 is 1 bigger than 1, we definitely have a slant asymptote. And to find that slant asymptote, we use polynomial long division. So x plus 1 goes into x squared. I'm going to leave space for my x term, which would be like 0x. I can even write in 0x plus 1. So we're taking the denominator and putting it into the numerator. So x goes into x squared. So what do you multiply x by to get x squared? Well, you multiply it by x. And x times x is x squared. X times 1 is x, and we subtract. The x squareds cancel out. 0x minus x is negative x. Bring down the plus 1. X goes into minus x minus 1 times. In other words, what do you multiply x by to get minus x? Well, you multiply by negative 1. Negative 1 times x is negative x. Negative 1 times 1 is negative 1. And we subtract. The minus x's cancel out. 1 minus negative 1 is 1 plus 1. That's 2. We don't really care about that right now. What we care about is this. Y equals x minus 1. That is our slant asymptote. Now, I didn't give you a problem like this, but if it turned out, if I gave you something like f of x equals x to the 4th plus 1 over, say, x plus 1, something like that, where the degree of the top is now 3 bigger than the degree of the bottom. If the degree of the top is more than 1 bigger than the degree of the bottom, this thing has no horizontal or slant asymptote. So if the degree of the top is 2 or more bigger than the degree of the bottom, in this case it's 3, then it has no slant asymptote at all. And looking at the last one, this is a polynomial. Polynomials have no asymptotes at all. And I said explain why. It's a polynomial. I think anybody reading that would certainly understand where you were coming from. Polynomials have no asymptotes, vertical, horizontal, slant of any sort. Okay, let's move on to the next page. So we want to sketch a graph. Let me move this over just a bit. We want to sketch a graph of 1 over x minus 1 and mark all intercepts and asymptotes and explain how you got the graph. I think maybe the easiest way to do this is just start off with a graph that we know we've committed to memory. Which is the graph y equals 1 over x. You know what that looks like. It has a branch over here, and it has a branch over here. We call that shape a hyperbola. And all we've done is we've taken the 1 and subtracted it from the x. You know that's a shift. When you add or subtract something to x, it's a horizontal shift, and horizontal shifts go opposite to the direction you'd expect. So in that case, you'd think minus 1 might mean to the left, but it's actually to the right. So we've shifted this whole thing 1 unit to the right. Let me draw this as carefully as I can. I'm going to draw it a little bit bigger. So y equals 1 over x minus 1. So we've shifted it over 1 unit to the right. Formerly, we had a vertical asymptote at 0. Now our vertical asymptote is going to be at x equals 1. So let me just dot that in. We've just shifted everything over to the right. That we still have the shape of a hyperbola here. Now you can see this thing didn't touch the x-axis before. It's not going to touch the x-axis now, so we don't have to worry about an x intercept. But we still have to worry about a y-intercept. We can see that it definitely does cross the y-axis. So for your y-intercept, we'll set x equals 0. When you get the x-intercept, you set y equals 0. When you get the y-intercept, you set x equals 0. So y, which is just equal to f of x, is 1 over, well, f of 0, I should say. F of 0, 1 over 0 minus 1. That's 1 over negative 1, or negative 1. We can see that this thing crosses the y-axis at negative 1. In a question like this, you want to definitely show all your work so that I can be sure that you did it yourself and it didn't just come out of a calculator. Okay, so on to number 4 now. We have a question all about exponential growth. So we have the number of cases of a particular disease during an epidemic grows exponentially. 1 week into the outbreak, there are 150 cases. 10 days into the outbreak, there are 250 cases. Find a formula for the number of cases as a function of the number of days since the outbreak. So let's go ahead and define some variables. Let's let t, lowercase t, be the number of days since the outbreak. So time since the outbreak in days. And let's let, I don't know, p, maybe c would have been a better choice, be the number of cases. I think I want c. Just changed my mind. So c is the number of cases. We're told that this is an exponential function, so c equals b times a to the t, where a and b are our numbers. So let's go ahead and find what a and b are. We have 2 pieces of information in the problem. When t is equal to 7, c is equal to 150. And when t is equal to 10, c is equal to 250. And hence, we have, let's put those numbers into our equation. I'm going to move this over just a little bit. We have, let's see, if I put 150 in for c, let me put the 150 in for c, we end up with 150 equals b times a to the 7th. And if I put 250 in for c, I have 250 equals b times a to the 10th. I just put t is 10 and c is 250 here, and t is 7 and b is and c is 150 here. Now I sort of have these upside down. What I want to do is take this and divide by that. So let me just rewrite those over here. So 250 equals b times a to the 10th, and 150 equals b times a to the 7th. I'm going to take this expression and divide by that expression. 250 divided by 150 is, 5/3, I guess. And the b's cancel out, and a to the 10th divided by a to the 7th is just a cubed. So a cubed is 5/3, so a is the cubed root of 5/3. I can go ahead and put that into my calculator. So let's see. We're going to take 5/3 and raise it to the power of 1/3, or in other words, take the cubed root. And I'm getting about 1.186. So approximately equal to 1.186. So I know now that my formula is c is equal to b times a was about 1.186 to the t. Now I can take either one of these points and put it back in for c and t and solve for b. So let's go ahead and use this one. I'll put c equals 150 equals b times 1.186 to the power 7. So I end up with b is equal to 150 divided by 1.186 to the power 7. Let's see what we get there. So 150 divided by 1.186 to the power 7. And I'm getting about 45.4. 45.4. And so now I know what B is, I know what A is, I can just go ahead and write my answer down. So C is equal to 45.4 times 1.186 to the power 7. Oh, sorry, to the power t. I want to have my variable there. So my variable is here, and my variable is here, and this is my final answer. I want to make sure that they're both those variables here. I defined those variables earlier. All this nonsense was to figure out what A and B were, and now that I have my answer. How many cases does our model predict there'll be 3 weeks after the outbreak? Well, I'm just going to plug in t equals 21 days. Remember, t is measured in days, and 3 weeks, I'm going to plug in 21. So the number of cases equals 45.4 times 1.186 to the power 21. And let's see what we get. 45.4 times 1.186 to the power 21. I'm getting 1,632 approximately. So this is approximately equal to 1,632. And there we go. All right, let's move on to question 5. So we have, oops, that should have said log 10. So I want log base 10 of 0.01. So I see I've made a mistake. Oh my goodness, these are all messed up. Okay, so let me tell you what the question was supposed to say. It was supposed to say log base 10 of 0.01. And I will go back and try to correct that in the original review sheet, but no wonder if you were confused. So 0.01, I'm looking for the number I have to raise 10 to give me the number 0.01. And the number I have to raise 10 to get 0.01 is -2, because 10 to the power -2 is 1 over 10 squared, or 1 over 100, which is 0.01. This is supposed to say log base 10 of, what is it, 10 to the 3,000. So pause it here now that you can see what the question is, or if you have it correct on your page because I've already corrected it, that's great. But if you haven't, if you had the incorrect version, go ahead and do the problem. Presumably you've paused it and done the problem. So what we're asking is, what power do you have to raise 10 to get 10 raised to the power 3,000? Well, you raise it to the power 3,000, of course. 10 raised to the power 3,000 is 10 raised to the power 3,000. And down here, this very last one on this page, log base 2 of the square root of 2, what power do you have to raise 2 to get the square root of 2? Well, you raise it to the power 1/2, because 2 to the 1/2 is the same as the square root of 2. Anything raised to the power 1/2 is the same as the square root of that number. And a few graphs here, y equals 2 to the x. I suppose you could work this out in real time if you want to, but we went through graphs exactly like this. You know that if the base of an exponential curve is greater than 1, that curve goes up to the right. It has the regular exponential shape. It approaches the x-axis asymptotically on the left and grows very rapidly on the right, and it crosses at 1. Can't imagine what anybody else would want in that picture. If we have g of x equals 2 to the x plus 1, that's exactly the same graph we had originally, but we just shifted up 1 unit. So instead of approaching y equals 0, which is the x-axis, asymptotically, Now we're approaching y equals 1. We're going to dot the asymptote in. The curve in A approached y equals 0. This one approaches y equals 1. And instead of crossing at y equals 1, it's going to cross 1 unit up at y equals 2. It's just the whole thing shifted up 1 unit. But it has the very same shape. And this curve is, again, the original curve that I had in A. I have a minus. You know it's a flip over one of the axes. If you have the minus in front of the whole function, it's going to flip it upside down. So the original curve flipped upside down. Instead of crossing at height 1, it's going to cross at height minus 1. And we have a curve that's just flipped upside down. The original curve from A flipped upside down. And in D, I have 1/2 to the x. You know that if the base is between 0 and 1, instead of being exponential growth, this is exponential decay. It's going to cross at height 1. It's basically just the mirror image of what we have in A. Sorry, my curve's so lumpy. I'm sure yours is nice and smooth. But it just crosses at 1 and goes downhill, approaches the positive x-axis asymptotically on the right. And that's it.